All right. Well, good afternoon, everyone. Thank you for joining me. My name is Jeremy Fairbank. Today we're going to talk about Elm. Elm is a functional programming language that compiles to JavaScript, and it provides us a really safe, robust way to build our front-end applications in a way that JavaScript itself really can't provide. So if you're interested in following me, I'm El Papapoyo on Twitter and J Fairbank on GitHub. Very briefly about me, I work for a company called Cgent. We're a completely remote team, or an agency focused on design and front-end development. And in addition to being an agency, we have our own product called Simply Built, which is a website builder and editor along with domain management and hosting. So front-end development has been undergoing a big boom over the past several years. And that's largely in part thanks to native web technologies and advances in the JavaScript engines. But with that has brought a host of problems as well, probably the most notable of which is JavaScript fatigue. So there are countless frameworks and options available these days to choose from, and it can be kind of intimidating. But at the same time, the reason why there's so many choices is because they're all trying to hone in on what are the best ways we can do front-end development and make building applications as easy as possible. So at the very least, through their collected efforts, we've kind of honed in on that MVC, two-way data binding structures just aren't really working on the front end, and they can lead to a lot of issues and bugs in our applications. So they've kind of migrated to this style of unidirectional architectures, model view update pattern, and a lot of reusable components. So not big classes and controllers, but really small composable components. But there's one thing, despite all their efforts, they haven't really fixed, and it's kind of hard to deal with. JavaScript, the language itself. Now, I've used JavaScript for many years. I still love JavaScript and do a lot of development in it. But we can't deny some of the problems that do live in JavaScript. One of the biggest, obviously, is null, or undefined is not a function. We've probably all fell prey to these type of errors, null reference errors, and they are a real issue. And JavaScript, even though we can write good, clean code, it's still the potential for something like this to happen if we're not careful. JavaScript is also impure and mutable. Now, we can write pure code and we can use immutable data structures, but it's still possible in the language. And some of the biggest problems that come from that are this idea that this function get named, for example. No matter how many times I invoke it, I'm never guaranteed I will always get back the string name, Jeremy. And that's because it's global state that's mutable. So we lose some confidence in our functions in JavaScript when we allow ourselves to write some impure functions with mutable state. APIs can be unsafe as well in JavaScript. So here I'm fetching a user. But what happens somewhere down the road, maybe that API payload changes. The shape changes of the user, and maybe it's not user.name anymore, it's maybe user.displayname. Or what if the whole payload itself changes and user is stuffed in maybe a data key? Well, this may not throw an error, and we may not find out there's a bug till later on, maybe in our view code when things aren't displaying properly. So we would have to write a lot of runtime validation code to make sure we always get the particular payload that we expect. Error handling can be a little cumbersome in JavaScript as well. So typically we would throw an error, but then we have to deal with try-catch blocks, worry that maybe some function from a third-party library could throw, and then that's going to just interrupt the whole execution of our program and unwrap the call stack. And in the asynchronous context, what if I leave out the catch callback on this promise? Well, if you know anything about promises and errors, it will inherently swallow errors, and you may not know about them. Thankfully, browsers are adding some warnings when this happens, but it's still something not built into JavaScript to make sure we deal with the potential for errors. So we have to do our due diligence. So is there anything we can do with all these issues with JavaScript? It's still a great language. Like I said, I love using it, but it has these problems. Is there a way we can address some of these issues, and build safe, robust web applications? And thankfully we can because of Elm. So Elm, as I mentioned, it's a functional programming language. It compiles to JavaScript, and it's strong statically typed. And we're going to learn from all these different benefits it offers that we can now build applications that we have a lot more confidence in. So from Elm's guides, it says, no runtime errors in practice, no null, no undefined is not a function. Those are very strong guarantees, but they are very promising if we can build applications and no longer have to worry about these types of issues. So let's look at Elm and see what is the benefit it's really given us. If I had to distill it down to one thing, I would say confidence. That I as a developer can now have confidence, or at least more confidence in the applications I build, that if my application compiles, more than likely it's correct and it's going to work properly, and I'm not going to have to deal with weird type coercion bugs or other things like that. And we get that because of the static typing, the expressive nature of Elm. It's going to inherently draw you to write smaller functions and write cleaner, more succinct code that you can understand better and have more productivity with. It's also terse, which is kind of like that. It's pure. It's immutable, and it has that unidirectional architecture that we talked about earlier. So let's start diving into Elm's syntax, learning about these benefits more, and see how they help raise our confidence level in the applications we build. So I mentioned Elm is a functional programming language, and what that essentially means is it's all built upon functions. Functions are our basic building block, and functions are inherently modular, reusable, and composable, because they only depend upon their arguments. They don't worry about global state. So they are more useful than just using classes and mutating some state in an object. So what do functions look like in Elm? So we typically define a function by giving an identifier. I have a greet function and an add function. It takes a list of arguments or parameters, but notice we separate them with white space. We don't use parentheses or commas, so it's a lot more terse and expressive. And then we just set the function equal to something, kind of like a variable. So we're saying it equal to a single expression. There's no concept of multiple statements and then a return keyword in Elm. So this inherently forces us to want to write smaller functions. And so this is code that's easier to read and understand. So our greet function, it takes a name and then it returns hello name by the concatenation operator. Our add function adds two numbers together. To invoke these functions, we do something similar. We have our identifier, and then we pass in the list of arguments, and we use white space there as well. So very concise, succinct syntax. And just an aside, this double dash here, that's how you do inline comments in Elm. So you'll see that in some of the code samples. So next, Elm functions are pure. And we've already hinted at that. And the idea is, my function only depends upon its arguments. It doesn't depend on global mutable state. And what the benefit of that is, it now gives me guarantees about when I invoke my function. For my add function, if I pass in 2 and 3 to it, I have a guarantee because it's pure and it depends only on its arguments, I always get back 5. Now imagine that at a much larger scale, where you have an application with lots of functions. You have a guarantee that whatever you pass into that function, you expect it to give back a certain value every time. That's such a universal concept in functional programming. We call it referential transparency, where it's this idea that I could technically replace every instance where I call add with 2, 3 here with just the number 5. And so this gives us a lot of those guarantees by being pure. We can take that concept even further with HTTP requests. So here at the top I have an Elm code sample for fetching a user, and on the bottom I have this JavaScript example for fetching a user. But the difference is that bottom one in JavaScript, that is impure. When I invoke fetch user, every invocation is going to be different because I'm affecting the outside world by immediately creating my HTTP request and dispatching it. The Elm code up top though, believe it or not, that actually doesn't dispatch an HTTP request. All it does is create a value. It's a pure function. So it's just going to create what we call a command, and we'll learn more about those as we dive into the architecture of Elm. But it's reproducible now. No matter how many times I call fetch user, I get back a command value that I expect. So if I wanted to test that function, I could test it a whole lot easier with a unit test than trying to test the function in JavaScript. Typically, we would need to use a mock server or something like that to deal with the JavaScript example. Elm is also declarative, and that's something that comes with functional programming, a declarative style where we want to declare what the desired result is. We're telling the computer what we want back, not how to do it. So to understand that, let's compare it with imperative style with this JavaScript code. We want to create a function that doubles the numbers of an array. So we're going to use a for loop in this example. You probably already know about the map function, but in this case we're going to write it in imperative style. Well, this just doesn't exist in Elm, and it's a lot more lines of code to write in imperative style. We're just giving a bunch of instructions to the computer. It's not inherently describing what it's really doing, which is doubling some numbers. In Elm, though, we can very succinctly describe this idea of doubling numbers. So we have what are called lists in Elm. They're kind of like arrays in JavaScript, but they're actually more like linked lists, so they're not something we can index into. But that's fine because we're typically just wanting to iterate over lists anyway. So now when I want to double numbers in Elm, I could define a simple function called double. It takes it in, and it returns n times 2. And then I can create the double numbers function, which takes a list. And in one line of code, I can do the same thing in a very expressive manner. I use this special list.map function that's in the Elm standard library. It takes 2 arguments, a mapping function, and a list to apply that mapping function to. So it's just going to apply the double function to every item in the list and produce a new list where every number is doubled. But notice how fewer lines of code it took. And we could write this in JavaScript with map as well, and I would definitely encourage that because we can accomplish a lot more with fewer lines of code, and typically we associate fewer lines of code with fewer chance of bugs. So this is a huge benefit. Elm functions are also curried. You've maybe heard of currying, and it may seem a little weird or hard to understand, but one way I like to think of it from a practical perspective, it's a way of creating building blocks. It's a way for us to just define really small focused functions, and then we can build more complex functions out of it. So to really understand that, let's first just get down the concept of currying so we can see what it means. So I could have this new add function that takes x, y, and z and returns the sum of all those. But really, I'm not taking 3 arguments. I'm taking 1 argument at a time and returning a new function. So what is happening, if I invoke add with 1, 2, and 3, really what happens is add takes in 1 argument, x. It returns a new function that now takes in the y. Once I invoke that with 2, I get back another function that takes in the value for z. Once all of those arguments are fulfilled, then we can invoke the expression, the function body, and get back our result. So a contrived way then we could use this as a building block is I could create an add1 function just from this add function. I pass in 1 to add, I get back a new function. And then later on I can invoke that with 2 and 3 and get back 6. Or I could take that further. Add3 could be made from invoking add1 with 2, and that gives me back a function that essentially invokes its argument or adds 3 to its argument. And we could do that to get back 6. So that's, as I admitted, a very contrived example, but let's take it back to the earlier thing we were doing with doubling numbers. We can actually reduce the lines of code in this one through currying. So remember that all functions are curried. That means the list.map function we have is curried. Remember, it takes 2 arguments, a mapping function and a list. Well, if I invoke list.map with double, I get back a new function that takes a list. So technically, I could just remove that parameter, and I still have the same function. I've just filled in the mapping function. I'm waiting to get the list. And so it's the same way to describe it, but with fewer lines of code. Now, could we apply that same thing with the double function? Crazy as it sounds, we can. Now, this is going to look really weird. Notice we're wrapping the multiplication operator in parentheses. Well, it turns out even operators in Elm are functions. And the way to think about that is your left operand is the first argument, and the right operand is your second argument. And so in Elm, I can wrap an operator with parentheses and get back a function that I can invoke like any other function. And since it's a curried function, when I invoke it with 2, I'm filling in the first left operand and getting back a function that's waiting on the second operand. So actually I could apply that concept to the double numbers function and reduce it down to just this. So the point is, we don't have to write all these functions out. I would caution there are times when you may want to be more self-documenting and write certain functions, but we can accomplish a lot more with just simple curried functions and see how we can create the double numbers with just one line or 2 lines if you count the new line there. Now, one thing you might have thought of, if we do everything with functions, what happens when we need to apply multiple functions to something? So let's say here I want to take a list, I want to double every number, I want to filter it, leaving only those numbers greater than 6, and then I want to square every number. Well, if we were to try to do that with the syntax we've already learned, it would be really ugly looking and hard to read and understand, and that seems to go against the things I'm talking about, having a very terse, readable language. Well, we can use a special operator for this called the pipe operator to deal with this, because remember, functions and expressions are all just one expression for a function body. So we can introduce this operator called the pipe operator or the forward function application operator, which is a mouthful. But it's basically a bar and a greater than sign. And so you can think of it similar to in a Unix shell and how you pipe from one function or command to another. So it's the same thing. The operand to the left is going to get piped into the item on the right, which is going to be a function, and it's going to basically make it the last argument to the function on the right. And that's possible because these functions are curried. So a better way to understand that is, let's just watch how it would pipe through. So we take list, we pipe it down to this list.map with the double function, and that's essentially the same thing it's doing. So on the bottom we have equivalent code where we create a doubled list in a similar manner, just without piping. So now we have this doubled list, and we can pipe it through to the filter. And it may look confusing in this manner, but we're actually going to filter those numbers and leave only those greater than 6. So when we wrap that less than symbol, we're filling in the left operand, which means we're looking for things that 6 is less than. And that's how it's actually going to produce numbers greater than 6. So we have filtered, and now we pipe it through to square. And so that's how we use the pipe operator to deal with this issue of multiple functions being applied. And it does present a unique way to make it very readable, this idea of just transforming something in multiple steps. I mentioned that Elm is strong and statically typed, and so to elaborate on that more and how it benefits us, it's this idea of creating and adhering to contracts. So if you've done other languages that have strong static types, you kind of know what I mean. We can describe what types our program takes on, and if it doesn't match, then it doesn't compile, and so it cannot run. I hadn't really showed that yet in Elm, because Elm can actually infer types pretty well, but it does strongly prefer if you provide types. So to define a type, you have your identifier, you have colon, and then you have the type, and then you give its value. So we have our normal integers, strings, and booleans, and then for a list, we would say list int. And obviously that list can only have int values in it when we say it's a list of int. Now to type functions, we're going to introduce arrows, which is, if you come from a language that uses lambdas with arrows, that kind of makes sense why we would use an arrow here. But we're essentially saying for greet, it takes a string and it returns a string. And then add, notice it has 2 arrows here, and that may be a little confusing, but remember, these are curried functions, and so this can help enforce that idea of we take one argument at a time. So I take an int, and I'm actually returning a function that takes an int. And that function finally returns an int. So the way to maybe make that more readable is we could wrap that last part in parentheses, and we see int returns a function that takes an int. So what's the benefit of typing, though, on all this boilerplate? Well, now, if I try to invoke the greet function with a boolean or add with even just a string, my code will not compile. I can't even run it. So compare that to JavaScript, though. If I accidentally pass in the wrong number of arguments or the wrong types, either it's going to blow up at runtime or it's just going to produce some weird type coercion bugs. We can avoid all of those bugs right at the start by not allowing the application to compile thanks to strong static types. That's really beneficial. So we've looked at some primitive types, but for real applications, we're probably going to have more complex types. that we need to use. So let's start walking through an example of how we can get into some more of the complex types in Elm. So let's say we want to create a dog type. Well, we could use tuples for this, and this is going to be, our dog type will have a name and an age, so a string and an integer. If you're a Python dev, you're probably familiar with tuples. It's a way to organize types together, essentially. So my dog is going to be a string and an int, and we group them together with parentheses. And then to create the dog, we use the parentheses with the values. Tucker is the name, 11 is the age. And then to operate on our type, we could use the special tuple functions from Elm. Tuple.first returns the first value, tuple.second returns the second value. Now this will work for really simple types, but when we need to add more properties to our dog, this could get really unwieldy and hard to actually access our values. So let's say we wanted to add a breed to our dog now. Well, now we could reach for maybe the record type instead. So this is very similar to objects in JavaScript. Notice we have the curly brace syntax like a JavaScript object. So when we type it, we could have name, string, age int, breed is going to be a string. So we just use colons to separate the key type pairs, each of those with a comma. And then to instantiate our record, we use the curly brace syntax with key value pairs separated with equal signs. So to access properties, we can still use dot access syntax like JavaScript. So that's really nice and useful. But notice here, I can actually put dot name, then dog. Well, it turns out, just like operators, record access is also a function in Elm. So when I say dot name, Elm's going to create a function for me that knows to take a record and pull out the name property of that record. So one really beneficial use for this is if we had a list of dogs and we wanted to pull out every name for every dog, we could easily write list.map.name and then the list of dogs. With one line, we can pull out every name of every dog thanks to this special record access. Now, typing with records could be a little cumbersome. Every time if we want to create a dog, we have to type out that long curly brace to declare what its type is. So one way we can get around this is to create our own dog type via type aliasing. So Elm gives you these two keywords, type and alias. We can declare this uppercase dog type and say it's the same as a record of this type with a name, age, and a breed. And now when I want to declare the type of any of instances of my dog, I use my uppercase dog, and then I can instantiate it with the record syntax. But Elm actually even gives us a constructor function for that, a more succinct way to create these records. And this is through type aliasing. And it works because this function, the order of arguments, matches the order of the properties that I declared in the original record. So name is first, age is second, and breed is third. So this is nice and convenient. Now when I want to update a dog though, we're going to have to deal with immutability in Elm. And the idea is we want to create state. We don't want to mutate it, which is possible in JavaScript. And the main benefit of that is if we prevent mutation, we can ideally prevent a lot of bugs that we could encounter when we accidentally mutate some state we didn't mean to, or we can get into some incorrect configuration in our programs. So if I wanted to update my dog, maybe the dog wants to have a birthday. Well, instead, I'm going to create a new dog, and I'm going to use this special merge syntax, which is kind of similar to maybe object.assign, or if you use some future JavaScript features like the spread operator in objects. So I have the curly braces in a bar, and what I'm saying is, take the original dog, all of the properties that are in it, use those, and then to the right of the bar I can specify every property I want to change for this new instance of the dog. So in this case I'll say its age is 1 plus the original dog's age. But now notice when I access dog.age, age has stayed the same. We did not mutate the original dog. But our new dog, its age is 12. And that's thanks to this special merge syntax, and it prevents us from having any mutation in our programs that could lead to bugs. Now one thing you might have thought of with our breed inside of our dog, why are we using a string here? If we had a program where we wanted to confine what values breed can take on, you would have to imagine we'd have to write some runtime validation code to make sure that when we type Sheltie, it's spelled a certain way, and then any other breeds we want to take in are the only values accepted. But that's something we have to worry about at runtime. And so that's extra code we have to write. We'd like if the Elm type checker could work for us in this regard. And so we can do that thanks to union types as well. So union types are different from aliases in that we can create a new type and define what values it can take on. And this idea is that we know breed is a finite concept. There are only so many breeds. So we can force breed to be type checked now in Elm instead of having to worry about lots of runtime validation code to make sure the breed confines to a certain value we want. So union types, to define them, we'll have the type keyword with the name of the type. We'll say it's equal to a set of values. First, it's a sheltie, and then we can use bar to then specify any other value it can take on. So this is sheltie or corgi or golden retriever or a mix of a breed and a breed. And then when we want to use this type with our dogs, we just use those values we defined. So Elm actually gives us constructor functions for these as well. So I just say this dog is a sheltie. This dog's a corgi. Well, what about the third dog? We know it's a mix, but this actually won't be fully typed. And notice up there we have a mix of breed and breed. And so if these are constructor functions, like normal functions, they can take arguments as well. So we're saying that a mix has to be of two different breeds. So that means I need to invoke mix with the two different breeds I have. So not only do I have a finite list, I can still allow mixes of breeds, and so types can be recursive in that regard. So you could use a union type for, say, creating your own linked list with nodes or a tree type structure. Or union types are really beneficial for maybe a finite state machine where you define all the particular states that your program can take on. And then you can type check that, which is really nice. So one other thing we haven't really addressed is we said Elm doesn't have a null, but we obviously all know in software development, null-like situations happen. What if I fetch a user from a database and that user doesn't exist? That's a real-world situation that is probably going to happen. And if Elm doesn't have a null, how do we deal with this situation? Well, we can do that with a special union type that Elm defines for us called maybe. And this is its literal definition in Elm source code. So you can look at it as maybe I have this or maybe I don't. So the values it takes on is either I just have this thing, just have a user, just have a dog, or I have nothing. And so the way we write that is we introduce this little thing called a type parameter. We're going to let the stand-in for it be just a lowercase a. But maybe is a boxing type. And it's going to box over whatever value we either have or we don't. And so A is a stand-in for saying that this could take on any type. So it's kind of like a generic, so to speak. So a contrived example of how maybe we could use maybe is if I have a divide function that takes in two numbers, numerator, denominator, then divides them. Well, we know that we can't divide by 0, so we could use maybe to deal with the situation. If that's an undefined situation, then we have nothing. So for the declared type, we'll return a maybe of a float. And then when we check if our denominator is 0, then we're going to return nothing. This is invalid, so we're going to deal with it by using a maybe and returning this nothing. Yes? We'll get to that. Upcoming slides, but good question. Now otherwise, we'll do the division and we'll wrap it in a just. And so when we divide 4 by 2, we get just of 2. If we divide 4 by 0, though, an undefined situation, we're just going to return nothing. And so what's the benefit of that? And also, how do we get to the value that's wrapped by a just? Well, we use something called pattern matching. And so pattern matching with this case of expression is like a really powerful version of a switch statement in an imperative language like JavaScript or Java. And so we say case of something, so we give the expression, and then we have several branches, so like your case statements in a switch statement. So we either have just and what pattern matching lets me do is I can now access the value inside that just and bind it to a variable called in. And then I'll return a string, result is concatenated with toString of in. And for the nothing branch, I'll just return no result. So now we've dealt with I had it or I didn't. Now what happens though if we say, well, I don't think that nothing situation is ever going to happen. There's going to be null, it's going to be fine. Well, it turns out Elm won't let you do that. If I leave out the nothing branch here in this case expression, it will not compile. So Elm is forcing you to deal with the null situation. And so if you compare that with JavaScript, a lot of times we may think we'll never deal with that situation, and maybe we really won't. So we can get away with that. Elm's not going to allow you to do that. It's going to force you to deal with those situations where nothing does exist. So I hope that's kind of what you were looking for. So it's mainly the type benefits of it, that you can box these values in and be forced to deal with these situations, and it can catch it for you at type or at compile time. So that's kind of a quick deep dive in some of the syntax and benefits of Elm. I want to cover just a couple brief things and then start looking at its architecture and see how that really works to build applications with Elm. So Elm has some built-in tooling, which is a nice perk over JavaScript where we have to add in lots of features. It has a package manager, a compiler, a REPL, and a dev server. It also has its own built-in framework, which is the architecture that we'll look at next. But compare that to a lot of the JavaScript fatigue issues where I have JavaScript and now I have to pick what framework I want to use, what tooling I need to use, whether Babel, TypeScript, Webpack, etc. Well, I get most of all of that built in right with Elm, and I don't have to worry about making all these choices anymore. So what does this architecture look like? Well, it's what we call the model view update pattern. And it's a very unidirectional pattern. I have state, my model. I have a view, and that is just a reflection of my state, displaying it. My view doesn't have business logic. It doesn't have its own state. So all the state is consolidated in one area. And then any changes to that state happen in the update phase. So we have organized how the data flows in our application in one way, and we also organize the communication through messages that we'll look at further. So when you have an Elm application, it's going to look sort of like this at a high level. Your application is going to sit inside the shell of Elm. And it's going to manage your model, your state on your behalf. And then any communication that your application wants to do with the outside world has to go through Elm. And so that allows you to only focus on writing pure functions in Elm, including your HTML. You're not writing real HTML, you're writing virtual DOM, which is just pure values, and Elm handles that for you to actually build the DOM HTML. So what are some of the communication channels, so to speak? Elm has commands. We've briefly mentioned that with HTTP requests, but that's a way where you can pass off a command value to Elm, and it can handle HTTP for you. You can also subscribe to things like WebSockets or browser resizes and many other things, and Elm will handle that on your behalf as well. And also DOM events, whether that's on clicks or text input. And so what Elm's going to do is anything you're interested in listening to, which you just give to Elm as a pure value, it'll create a task in the background. And then eventually, once that's fulfilled, it's going to give back a message to you. Now this message is a message type that you define. So you're not only providing a model view update and issuing commands and whatnot, but you're also defining here are the only ways that I expect to communicate, and that's through messages. And we'll see that when we look at a demo. So kind of blowing this up to see how these communications happen, we obviously, as we said, we give state to Elm. This is the state we want it to manage on our behalf. We give it that update function, which updates the state, and also we will use for issuing commands, and then the view layer for displaying it. So the life cycle of all this is Elm takes your state, uses your view function, everything you write is pure functions that you can test, and then Elm manages creating the HTML and the DOM nodes for you. If there's an event from the browser, let's say the user wants to change the color of this car to red, then it's going to notify, that event's going to go to Elm first. Elm is then going to look for the message type that you said you were interested in listening to this particular event when the color changes. And it's going to use your update function to supply it with the message that says we're changing the color, and it'll provide the current state, the blue car. Your update function is then going to use that to know to return a red car now as the new state and give that back to Elm. And then Elm can use that to then use the view layer to display this red car. So see, everything's unidirectional going in one pathway. And so to make more sense of that, we're going to dive into the architecture now and see how we really build an app with this architecture. So we're going to build a simple just Twitter client for loading a user's profile. And we'll be responsible for typing in the username and then clicking load to load it up. So we'll see how we deal with HTTP in Elm. So first off, every file in Elm is a module, so it's a very modular language. So we first need to declare a module. This is going to be the profile module. We'll have a module keyword, the name of our module, and then we'll have this exposing keyword, so we can specify what we really want to expose in our module. So if I defined a couple things like fn1, fn2, I could make them specific, or I can just use this double dot syntax, which is like a wildcard, or rather to say, expose every function I define. Since it's modular, I can also import other modules. I'm going to import the HTML module here, which we'll use for building the virtual DOM. And notice I'm exposing everything that it defines. So it primarily defines like an HTML type, and it defines functions for every tag. There's a div tag, a paragraph tag, an anchor tag, but these are all functions that we're going to use to produce values and give back to Elm so it can be responsible for the real HTML DOM. Like most programming languages, we're going to have a main function. For this very simple start, it's just going to be typed as an HTML of message. And we'll learn more about messages once we really start building our app. We're setting it equal then to a div, or a call to div. And every HTML function takes two arguments. The first is a list of attributes. So this would be like class, ID, onClick, etc. The second list here is any children. So this is how you start to compose your view and your tags together. So this could be any number of children for this div tag. In this case, I'm going to use just a text node. And this text function comes from the HTML module as well. But now we want to turn this into a real application. So we're going to change the types. It's going to be a program. And it's going to have several type parameters. The first one is flags. And we're not using any flags for our program, so we'll say never. It's a special type in Elm. We're going to have a model type that we'll define, and we'll have our messages, the ways we communicate back and forth with the outside world. So we're going to have to define those two types. To create a program, we'll call the HTML program function. It takes a record with several properties. It has a init, view, update, and subscriptions. So we talked about view and update. We have to provide those. Init is a way of providing our initial state as well as providing an initial command. Like if we wanted Elm to immediately issue an HTTP request when our application boots. Subscriptions is something we won't use for this demo, but that would be a way for you to say, I want to listen to WebSocket events or something like that. So we're first going to need a model. Since this is a Twitter user, we have a screen name. And we want to store that in our model for this application because we're going to store it to use it later when we want to fetch a particular user. We need the message type. And that's going to be a union type because we have a confined set of the only types of messages we have in our program. And for now, I'm just going to fill it in with message again. I'm going to define an initial model for our Elm to know where to start. We'll use the constructor function it gives us from the alias, so the first parameter would be the screen name. Once we start off, we don't have one, so we'll use the empty string. We're going to define that in init, and that's going to be a tuple, a pair, of our initial model and of a command. So commands in Elm, they're of a type CMD, which is short for command. And they are parameterized by messages, because remember, we have to confine communication to our message type. So we'll give it the initial model here in this tuple, and we'll use the command none function to say we don't want to issue any commands initially. Our view, it's a function that takes our model and returns HTML of a message. It's HTML of a message because we can also subscribe to DOM events, and that's again confined by the message type that we define. And so notice here, view, it's a reflection of our model, so that's why model is its parameter. So I'm going to create a view for typing in the screen name for right now and saving it in our state. So I want to give it a class of load profile, which means I'm going to have to import the attributes model. And that's just going to provide all the functions we might want for defining attributes for HTML. So I'm going to end up using class, source, type, value, and disabled for this program. Now for the children of this, I'll have an h4 tag, it'll have load profile. I have a label for the input. Screen name. And then an input element for typing. Be of type text. And we'll let its value be the model screen name. So even though we're going to be typing in it to supply the screen name, because we want that state to be in, or that screen name to be in our state, we're going to let this be a reflection of what was just typed in. We'll have a button. We want it to be disabled initially if the screen name is the empty string, because we don't want to fetch a user without a screen name. And then finally, I'm going to put a paragraph tag here, and that'll be a way for us to verify that we're actually going to display the screen name we just typed in to prove that it's in our program state. Next, we need the update function. It takes a message that we define, takes our current state, the model, and it's going to produce another of those tuples, which has any new state and any commands we want to issue. For now, we're not going to deal with this, so we're just going to return the same state and issue no command here. And finally, for subscriptions, it just takes model and returns sub of a message. And again, we're not using that in this example, so we'll just do sub.none. And notice here we have type error there, and that's fixed. I'm having an issue with my Vim wanting to recognize type errors there. But notice here, when I save, nothing's happening on the left. And I have an X over here on the left of my editor. And I intentionally introduced a bug here. So you notice this input we had here. Every other HTML, we've had the list of attributes and the list of children. We did not include that with input. So even mistyped HTML, where we forget a certain parameter, that's not going to type check, and so our program will not compile. Once I supply just that empty list there, everything's of the same type for these HTML nodes. I'll save, and everything loads up now. So now we have that type checking and that guarantee that everything has to compile before our program can even run. Now I'm typing in, notice nothing's showing up here in that paragraph tag. Our button is still disabled, so we're not updating state. So now we need a way to subscribe to this onInput event from our DOM, or our virtual DOM in this case. So we need this input to start notifying us. So we can use the onInput event function, and it's going to need a message type. So now we can start defining what are the messages that our program uses. I'm going to have an update screen name message. And so onInput wants a function, a constructor function, that it can invoke with basically event.target.value. And then that same message is going to get passed into our update function down here. So to get our events, we'll import the HTML events module. We'll also need onClick, but we're going to pull in those two functions. And they're functions like everything else. And now we can update the message type to use this update screen name message. Remember I said it needs to take a string, so we'll give it that parameter there. So now that we're going to be able to issue this event, whenever we type in the text box, we need to handle it. So I'm going to use pattern matching on my message, just like we did with maybe. In this case, we only have one, update screen name. And with pattern matching, we combine the value to this screen name variable. We'll create a new tuple with new state with the merge syntax. And then we'll issue no command in this case. Everything looks like it type checks, so we'll hit save. And now it loads up. There it's showing up in the paragraph tag, so we know we're saving it in the state, and the button's no longer disabled. Now when I click on the button, it's not working, so now I need to start working on how are we going to get this HTTP request to work, and how are we going to load the user up. So if we go to our button, we essentially want to be able to dispatch something here when we click. So we have the onClick that we imported earlier. We need to define a new message type. We're going to call it fetch user. So now we're saying whenever that button's clicked, please issue this fetch user message that I can handle in the update function. So we'll add to our union type fetch user. And we'll also go ahead and add a load user message as well. So once the user's loaded eventually, we need to get it back into our application. So we're going to define a message for that. Now it takes a result parameter. And I'm wrapping in parentheses because the result type itself takes a couple parameters. It takes an error type and a success type. Successful, we want a user. If there's an error, we're going to use an HTTP error. So what is this result type? We haven't seen that. It's basically a special case of maybe. And it takes on an OK value or an error value. And has two type parameters, error and value. So this is just like maybe, which had just and nothing. But instead of nothing not wrapping anything, now it's going to wrap an error. So this is a useful way to do a success failure, where if it's a failure, that error value right here, which can be any type, is like a reason code or an explanation message for why this failed, like the user wasn't found. So we'll need the HTTP module. We'll need a user type. So we'll use another alias here. Obviously, this will be a screen name because we're going to be loading a Twitter user. We'll also load their name, description of the user, and their profile image. Now we need to store this user in our state. We're going to put it under a profile key. But do we want to use the user type right here? If we go down to our initial model, we need to make sure we add a profile to it. We would essentially have to provide it with an initial user, but that's not really valid. We don't want to create just a fake user here. Really, we have a situation where either we have a user or we don't. So that actually sounds like maybe we have a user, which means initially we have nothing. So now we can start updating our view layer to deal with whether we have a user or not. And we'll use some little bit of composition or composable views here. So I want to change this to be a load profile view, the view we were using before, where we type in the screen name. And that's the case where we don't have a user yet. When we do have a user though, let's use a function called profile view that takes a user and returns HTML. I'm going to use a let expression here, which we really didn't discuss, but it's basically a way for you to introduce custom bindings, like custom variables, inside the body of your function. But it's all one single expression. We'll let that be the user's name, concatenated with their screen name, in parentheses. And inside here, we'll have a div with class profile. We'll have their image tag for their profile image. Inside here we'll have a h3 tag. We'll use that binding we created for display name. And then finally we'll display a description of the user. So now we have two separate views to deal with these different situations. Now notice though, this isn't going to type yet. We have an error down here at view now. We got rid of view because we separated it out into two different views. So now we need to compose over them. So we'll create a new view. And now we can build upon this idea of whether we have a user right now or not by using pattern matching. So we'll use pattern matching over model.profile. If we just have a user, then we'll use the profile view with that user. If we have nothing, then we'll use that load profile view with the model. We should be getting, a type error here. Oh, type checker caught me. Needs to be under source in the attributes there. Now also, we're not going to type. Remember how I mentioned with pattern matching, when you use it on a union type, which is our message, it requires all branches to be considered. Right now, we're only handling update screen name. But if we go down here to this update function, at the very bottom there, I don't know if you can read that or not, it says this case does not have branches for all possibilities. So it's making sure we handle all the possibilities with our message, because that's the way we handle communication in our application. So if we have fetch user, we're not changing state in this case, but remember we also use the update function for issuing commands. So we're going to need sort of a fetch user function that takes the model screen name. So we need to define this function for creating an HTTP command. So that's going to take a string, which is the screen name, and it needs to return a command of our message types. Take the screen name. We're going to use another let expression here. We need a URL for where the user API is. And then we're going to create a request. We're not going to issue the request because everything is a value in Elm. We're going to use the HTTP GET function, and it takes that URL we just created. It also takes something else that we're going to call a user decoder. And this may be one of the most confusing parts of this, but there's a good reason for why we need to define what we call a decoder here. So remember, we're going to have some random JSON payload. We can't necessarily trust it, but we know it has to adhere to a certain shape that we expect because it has to enter our world of static types. So we need to translate this JSON payload somehow to our user type. So to deal with that, we can create a decoder. That's going to require the JSON decode module, which has a couple functions, string and then, well, a decoder type. And then this third-party pipeline module, which has required and decode. And that's a lot of random functions in a type. We'll see how we use them. And it's going to hopefully look a little readable and understandable still what we're trying to accomplish. So we'll come down here. We need to define this user decoder. It's going to be a decoder of our user. We're going to say, I want to decode this user type, and here's how I'm going to recreate it from the JSON. We're going to use piping. We're going to use that required function from the pipeline module. We're going to say it takes a screen name, and it's a string. And so that's where all those functions are going to come into play. And this pipeline allows us to structure it in the same order that we defined for our user type. So we'll have name, description, and profile image URL. See, we've mimicked the user type and how we defined each property. But what this pipeline module allows us to do is to say screen name is required, name is required, description, etc. And they're all strings. In fact, the string we supply here is what the property is in the payload. Twitter's API uses underscores here, but internally in our type we're using camel case. But what it's saying is, it's going to look, when it gets that payload, it's going to look for screen name. If it finds it, then it's going to first invoke user with that. Same thing with name. Once it finds name, it's then going to add that as the second parameter. And so this is a way for us to tell it, here's how you find what the payload has and convert it into my type. So now we can go back to our fetch user. We have the decoder, which means we have a request. It's a value, not the actual HTTP request. And then we can send it off with the HTTP send function. Now, once this is sent, we need to be notified once we have our user back. So we need to provide it with the type, load user that we define. That's the message we want to know when the user comes back. And then we're going to provide it with the request, and that'll create our fetch user. Finally, in our update function, we need to handle load user. We'll grab the result. Remember, it's this special certain type of maybe with OK and error. So we can use pattern matching on that. If it's OK, it's successful, we can grab the user, create a new state where profile is equal to just that user. And then I'm going to cheat a little here. For the error case, since we don't have time to really dive into writing code for it, we're just going to ignore it. But we would definitely want to handle that case and do something. And so we'll just return the same state and not issue any new commands. So everything looks like it's compiling now. We'll save it. Look at our network. It's really blown up here. Type in the pop-up Poyo. And there it loads up. So basically what we've done is we've written a bunch of pure functions that just describe our UI, describe how we want to fetch a user, and we've handed all that off to Elm, and it's done everything for us. And once it's loaded the user, it's given it back to us. But let's go back just for a minute and see how would Elm deal with what happens if the payload isn't what we expect. So I'm going to import the debug library and its log function. It's probably the only impure function in Elm because it does allow you to log to the console. But if I go to my decoder, and let's say instead of name, I thought it had display name. Now this will type check and compile because we can't check the API ahead of time. But if I hit save here, in fact I need to make sure I log out what we have here. If I try to load myself now, nothing happens. It's maybe a little hard to read, but when I logged it out, instead of getting the OK, we got an error now. It says bad payload. This is the message, why it failed. Expecting an object with a field name display name, but instead got, and in this case it's just logging out the entire raw JSON. But this guarded us from that API payload change. So now we can immediately know there's a problem, the API has changed, we have to deal with this error, and it hopefully is going to prevent any issues coming down the pipeline that might happen in JavaScript. So we'll quickly revert that, just to make sure it still runs. And everything loads up fine. So that was kind of a quick deep dive into looking at Elm, its architecture, its types, syntax, and I'm sure it's a lot to take in. It's a lot to put together in a 1-hour talk. But despite what seems like a lot of boilerplate, I hope the main takeaway you can see from this is that we can structure everything in our code. Everything is type checked, and if it doesn't compile, then our program has an issue with it. And so we've been able to prevent any runtime exceptions from happening. We even type check issues where we don't have something or we do, and even we're guarding against bad API payloads, all within the language. We haven't added any special frameworks or libraries. And so Elm provides a lot for us to write these safe, robust web applications that unfortunately JavaScript just can't fully guarantee for us. So thank you so much for attending, and I really hope you enjoyed it. There's a few links for Elm's documentation and the language itself, how to get installed and up and rolling, and then some links to the code that you saw today and these slides. Thank you all so much.